Now onto the fun questions, equilibrium problems. These particular questions are asked every single year on the AP exam. In fact, it's always the first question of Part 2, which is good because at least we know it's coming. What kinds of questions might you see? Well, let's go forward and we will find out. All right, here we go. Consider the reaction represented by this equation. And in the beginning, we're going to do trial number 1. 6 molar iron and 10 molar SCN are mixed at a certain temperature, and an equilibrium concentration of FeSCN is 4 molar. What is the value for the equilibrium constant for this reaction? All right, this is one of those kind where you have something in the beginning and then something later on. And you might be thinking, well, it might just be products over reactants, because of course that's what equilibrium is, concentration of the products over the concentration of reactants. And that's true, but you notice the 6 molar and the 10 molar are in the beginning. They are not at equilibrium. So how do we do this question? So there's those two. And 4 molar is at a later date and time. So we do our famous ICE table. And ICE, remember, stands for initial, change, and equilibrium. So let's see what happened. You notice in the beginning we have 6 molar Fe, 10 molar SCN, and of course in the beginning we don't have any products. I think from an earlier diagram we saw that in the beginning you never have any products. Now, we know in the end, or at equilibrium, we ended up with 4 molar FeSCN. So that means the change was 4, and this must have lost 4 as well as this one. Where do we get these numbers? We get these numbers by ratio. The mole ratio between iron, the SCN, and the FeSCN are all 1 to 1 to 1. So the change column are all going to contain the same numbers. Remember, we always lose from the reactants and give to the products. So that's why these are minus, and this one's plus. So in the end, you can notice we have 2 molar iron, 6 molar SCN, and of course 4 molar FeSCN. Now the question I think was, what's the value of K? Pretty easy, because all we have to do is now put products over reactants. And you notice nothing is raised to any power, and therefore you put 4 divided by the product of 2 and 6, and I think you get about a third. Let's see. Yep. K is 0.333. And again, remember, there is no unit for K. Alright, moving on to another kind of question. Same equation. We're going to look at another trial. And this time, you start with 10 molar iron and 8 molar SCN. Same situation as number 1. What is the equilibrium concentration of FeSCN? Well, we know that both of those are the initial concentration. So if you want to think of ice, initially we had 10.0 molar of that and 8.0 molar of that, 8.00, and we don't have any SCN. We want to know what the change is going to be. We do, however, know that our answer has to be what? What does that number have to be? What does the equilibrium constant have to be? From trial 1, because it's at the same temperature, we already know it has to be 0.333, or about 1/3. That's what our answer has to be. So we notice here that what could happen is, since we don't know this number, we don't know any of the change, we would look at the limiting reactant. So this is limiting, and let's see what we get here. This would be 2 molar. We wouldn't have any of that, and this would be plus 8.00, 8.00 molar. Now, if we plugged those numbers into products over reactants, let's see what we get. Well, using equilibrium concentrations, of course, it'd be 8 divided by 2, and of course that wouldn't count because it would have gone away. So 8 over 2 is 4. Well, 4 is clearly not equal to 1/3. So we know that the entire thing was not used up. The SCN was not fully used up. So the question is, what is the value of FESCN? You can solve it using x's, or by trial and error, at least at this point, when you work it out, you can find that the concentration of FESCN, as you will see, I will reveal, is 5 molar. Now, how on earth do they get that? Well, if this is 5, that means the change must be 5, and must be 5, and also change must be 5, and 8 minus 5 is 3, 10 minus 5 is 5. Now when you plug these concentrations in, you have 5 over 15, 5.00 over the product of 5 and 3, which is 15, and you get 1/3. So that is the answer in this case. You notice that the value that we had here, the Q, if you will, like we discussed in the last unit, the Q value is larger than it needs to be. And therefore, we're going to actually have to shift a bit to get the value of K smaller, which means we have to shift back to the left. We don't use quite as much FE and SCN as we thought initially. Same situation here. However, we have 6 molar of both reactants. And the question is, what is the concentration of FESCN? If we use ice again, and we use 6, and 6, and 0, and we assume the entire thing goes to completion, which means you'd be subtracting 6, and you'd have no product reactants. You'd be producing 6 molar FESCN. Putting it into the equilibrium expression, of course, that would be 6 over nothing, because not a 0. We could never do that in math. It would be 6. And again, that would be too big. So what we have to do is we have to realize that we can't take all 6 molar of the reactants away. We have to take a smaller amount away and produce a smaller amount of products. When you work it out, you will notice that the concentration of the FESCN is 3 molar. So that would mean, if this is 3, the change is also 3, and this is 3, which means this, 6 minus 3 is 3. Same here. Change is 3. And when you plug it in, you get 3 over 3.00 over 9, which is 1/3, or 0.0333. So again, that's another situation where reaction has to shift accordingly to produce the right value of K. All right, here's another example, or another overview of how to solve equilibrium problems. Write the balanced equation for the reaction. That's really important because, of course, the coefficients are often exponents. And if there aren't any coefficients, well, that's fine, but sometimes there are. Write the expression using the law of mass action. In other words, products over reactant, the generic one, the one with the brackets and the symbols for the compounds or elements. Then you list the initial concentrations, calculate Q, and determine the direction of shift to equilibrium. Define the change needed to reach equilibrium, and define the equilibrium concentrations by applying the change to the initial concentrations. So we can figure out what it is. Is it as big as we thought? Is it smaller? Etc. Substitute the equilibrium concentrations into the equilibrium expression and solve for the unknown. Check your calculated equilibrium concentrations by making sure they give you the correct value of K, which we did. Here's another reaction. Consider the reaction represented by, oh, surprise, same equation. Notice there are 3 trials. And again, what they're doing is we're trying to figure out the equilibrium concentrations for all species. Now, we already know the value of K from the first question. So the first thing we can do is we can plug in and see if we actually get the value of K. So let's check it out. All right, so nothing is squared, so I'm not going to worry about writing the mass action expression. It's just going to be the concentration of this divided by the products of that. So obviously the value of K, or Q, we will call it here, is 1 over 45. 1 over 45 is clearly not 1/3. So this number here is too small, and we will have to adjust accordingly. We're going to have to produce more products, actually. All right, let's check this out. 5 over 6. This number is too big. Almost feel like Goldilocks and the Three Bears. One was too small, one was too big, and what do you know, the next one, just like Goldilocks and the Three Bears, 2 times 9 is 18. That is 1/3. This is just right. So this last one is actually at equilibrium. But you can see if something is too small, we're going to have to increase the concentration of the products. If it's too big, we're going to have to decrease it. And if it's just right, we jump up in the air and say yippee-doo because we are right there. So let's see the answers, and you can try these on your own. With trial 1, you notice the amount of FeSCN did have to be increased, in fact, to 4 to make it work out. And for trial 2, again, had to be decreased to 4. And then finally, the third trial was just right, so we didn't have to do anything at all. So let's look at an example of a question you might see. A 2-mole sample of ammonia is introduced into a 1-liter container. At a certain temperature, the ammonia partially dissociates according to the equation. NH3 yields N2 plus H2. And the question asks, at equilibrium, 1 mole of ammonia remains. Calculate the value for K. Again, looks pretty easy. Here, we're also going to use ice, but the other thing to notice is this equation is not balanced. We have to make sure it's balanced. So I'm going to put a 3 here and a 2 here, and that will balance things up, which is going to make the mass action expression N2 times H2 to the third over NH3 squared. Okay, that's the value of K. We'll be plugging these numbers in. In the beginning, they tell you you have a 2-mole sample, and it's in a 1-liter container. Now that really helps out because we need molarity. 2 moles in 1 liter is 2 molar. So I'm going to cheat. I'll put my ice chart up here. And I'm going to call this 2.0 molar in the beginning because I don't like to have to calculate molarity later. In the beginning, of course, you don't have any products. At the end, however, you have 1 mole of ammonia. That means 1.0 molar remained. Now, you'll notice the coefficients. We don't know the change, but we know that it's equal to, the change is 1.0 molar, which is totally fine. Notice it's 2 to 1 to 3. So I'm going to say 2x equals that, x equals that, and 3x equals that change. That sometimes will help me remember that these things are in ratio. So therefore, if 2x is 1 molar, obviously x is 0.5, and 3x is 1.5. So this is 1.5, this is 0.5, and remember these are added, and this is subtracted, and that's how we got that. When I plug all of these numbers of equilibrium into that, I should get exactly what they're going to tell me. Oh, they're going through some fancy boxing. Let them do that. In a 1-liter container, 1 mole, right? 1.69. And that's what I got when I worked it out. So that's how you do it. Pretty straightforward. Do make sure to balance, do make sure to make a mass action expression, and then solve for K. Okay. A 1 mole sample of N2O4 is placed in a 10-liter vessel and allowed to reach equilibrium according to this equation here. Notice it's a 1 to 2 ratio. This time it's 1 over 10 because it's 1 mole in 10 liters. So this is 0.1 molar. That's the initial. We don't have any product. And let's see what else they are asking. Oh dear, I've written in over top. I'm so sorry. I'm going to get rid of that. K is 4 times 10 to the negative 4. So here they give you the value of K, which is pretty nice. Now they want you to calculate the equilibrium concentrations of N2O4 and NO2. So pretty straightforward. again, what you're going to do is you're going to realize, again, ice, I'll try to slip it in here. This is 0.1 for the reason I said earlier. We know the change is x, and this is plus 2x. So this is 2x, and this is 0.1 minus x. And that equals the number 4 times 10 to the negative 4. That equals 2x over 0.1 minus x. And you can solve this question if you care to. And Bo, don't forget, I always seem to do this. It's 2x squared, because remember, when we plug it into the generic, let me rewrite it. We write NO2 with the square brackets squared over N2O4. See, if I'm too fast, like I was trying to be, I forget to square. So, and sometimes people think, well, I've already dealt with the squaring or whatever because there's a coefficient of a 2 and I doubled 2x. Isn't that enough? The answer is nope, it's not enough. So, in any case, this is our correct equation. And we could use a quadratic formula, somewhat of a nightmare to use, but you could do it. And if you have a TI-89 calculator like I do, you can actually just plug it in because there's a quadratic solver. Or if you have a quadratic equation solver on your other TI calculator, you can plug in A, B, and C, and that's no problem. Or magic. Well, not really. It's the 5% rule. If we know that the value of x is going to be a very teeny number next to 0.1, we can just actually scratch it out here because it's not going to make a big difference if we include it or not. And that's exactly what happens here. Usually that's what happens. In fact, in the recent probably 15 or 20 years of this exam that I've looked at, you've never had to use a quadratic. So the 5% rule is pretty nice. So essentially what you get when you solve for x, I got 0.00316. 0.00316 molar. That's the change between N2O4 and that. So therefore, oh, they're going for the boxing. Yes. All right. So therefore, to get my concentration of N2O4 at equilibrium, I have to say 0.1 minus 0.00316, and that's how I got 0.097. And of course, the other one is increasing, and I got 6.32 times 10 to the negative third, because that's 0.00316 times 2.